Okay, what we're going to do now is we're going to move on from sampling distributions of one proportion to sampling distributions of two proportions. So what we did last week was we said, hey, we're trying to figure out what the true proportion is of something. So what we're going to do is we're going to design a process where we're going to randomly select a sample of a fixed size. We're going to count the number of successes, and what we're going to do is get a little p hat from that. What the p hat does is it gives us an estimate, a sample, and we repeat that process over and over again, and we stack those p hats up. It's when we put little stickers up on the board for the Reese's Pieces, and eventually all of a sudden we saw a shape that started to form. We noticed that it was centered right around 40%. So that was where we used our estimate. So what we're doing today is we're going to do the same idea, but we're going to do two proportions. So the idea of this one is we're going to take samples from two different populations, and we're going to compare those proportions to each other. We're going to do it the same way. So like what we did before, where we took a sample of a size and we counted the number of successes, we're going to just do that twice, and we're going to look at the difference between the two. So let's go ahead and take a look and see how this process works. So what we're going to look at is we're looking here at do Skittles have or M&Ms have more orange candies? So what we're going to do is we're going to go through the process of taking samples of 50 Skittles and samples of 50 M&Ms virtually and try and figure it out. So here's what I mean. What's going to happen is you're going to go and jump to here. So what I'm going to do is I'm going to reset that. And what I'm going to do is I'm going to go ahead and I'm going to say, 20% of them are orange. We're going to take 50 Skittles. So we're going to go ahead and draw a sample. And we find out is that 11. So what that says is that's going to be 11 of the 50, or 22%, are going to be my p hat Skittles. Now what I'm going to do is I'm going to repeat the process, and I'm going to take some M&Ms. So in this case, I got 13 out of 50. 13 out of 50. Here to look at it. 13 out of 50, or 0.26, and that's going to be my p hat of M&Ms. So now what I want to look at is I actually want to look at the difference between those two. I want to do p hat Skittles minus p hat M&Ms, and in that case, what it's going to be is it's going to be 0.22 minus 0.26 equals negative 0.04. Okay, so now what's going to happen is we're going to go and put a little dot down here at 0.4. Or negative 0.4. What's going to happen is we're going to keep doing this over and over and over again. What we're going to do is we're going to take a sampling distribution of p hat Skittles minus p hat M&Ms. And what I want to do is I want to do this a whole lot of times. So what ends up happening, I'm just making up the data. Let's say that all of a sudden I look at something and it looks like this. So make sure I got it. I ran this a little ahead of time. So what we're going to do is we're going to look at this. 0.2 and 0.04 is 1, 2, 3, 4, and 06, 1, 2, 08, 1, 2, 01, and then 1, 2. So let me blow that up so you can look at that a little bit clearer. Okay, so here's my sampling distribution of p hat S minus p hat M, p hat Skittles minus p hat M&Ms, and that's what each one of these little dots are. Each one of these dots is the difference in proportions of orange candies for one sample of Skittles and one sample of M&Ms. One sample of M&Ms. Okay, so now if we go ahead and we look at this dot plot, what we're going to do is, if we're making predictions about it, what we did last time is roughly symmetric. But remember, when we did this, we actually said, we thought this thing could be approximately normal. And if I wanted to go ahead and say what the center of this is, well, if I look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 dots there. Okay, so we got 30 dots. So the middle one would be 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So to me, it looks like that sample is right there at 0, or most likely at 0.02. And what does our variability look like in terms of the spread? Well, if we kind of go off here, we go from 0.02 to 0.12, we go from 0.02 to negative 0.8. So if you kind of think about it, it's like that variability, if we're going to kind of ballpark it, I guess maybe about 0.05 would be our variability. So now what we're going to do is we're actually going to dig into it a little bit and see what the real numbers are. Well, what I'm going to tell you is the real numbers are, in terms of Google search, is that the P of Skittles is 0.216. They're 21.6% orange in Skittles. The P of M&Ms is 0.20, 20% of that. So now what we're going to do is we're going to go through, we're going to look at the shape. So the first thing is the shape. And the way we figure out shape is we have to do the NP thing. So what we're going to do is we're going to do N times P of Skittles. So in this case, we're going to do 50 times 0.216. That gives me 10.8. That's greater than or equal to 10. And I'm going to do N1 minus P Skittles, and that's going to be 50 times 1 minus 0.216. That's going to be 39.2. That's greater than or equal to 10. So I know this guy's going to be approximately normal. I'm going to repeat the process here. I'm going to do N times probability of M&Ms in this case. So 50, I'd expect 10 of them, which is greater than or equal to 10. I'm going to see how many failures I have. In this case, how many that are not orange. 50 times 1 minus 0.2. That's going to give me 40. That's greater than or equal to 10. So again, what I can say is since both of those numbers are true, I can describe both of these shapes as approximately normal. Now the means. What I can say is this random? The big question on this guy is this random? And theoretically, we're just going to go under the assumption that scooping up M&Ms, scooping up Skittles out of a bucket is a random process. So since this thing is random, we can now say that the mean of all of those P hats is going to be equal to the real proportion of Skittles, which is 0.216. So in this case, we do the same check for M&Ms. Again, we're assuming that it's random. We're going to go there. That's the only thing we can do. Unbiased estimator. We're assuming it's random. So the mean of the sampling distribution of all these M&Ms is going to be equal to the real one, which is 0.2. So, and this is on your formula sheet. The formula sheet says the mean of P hat equals P. Okay, so now we're going to do our standard deviation. Our standard deviation is a 10% check. So what I need to do is I need to say, is this number, so the way I'm going to do it is I'm going to take 10 times my sample, 10 times my sample for Skittles. So in this case, 10 times 50 is 500. Do you think it's safe to say there are more than 500 Skittles in the world? So in this one, I'm going to say safe to assume more than 500 Skittles. So now what I can now do is I can use this formula from my formula sheet. It's equal to the standard deviation of the sampling distribution is equal to, sorry, P times PS, 1 minus PS over N. So it's going to be equal to 0.216 times 1 minus 0.216 over 50. So what that tells me is that the standard deviation is going to be 0.0582. And now what I want to do is I want to go ahead and do the same process over here for M&Ms, and it's going to be the same. If you think about it, we're going to say that we need to have, it's safe to assume more than 500 M&Ms. So again, what this allows me to do is it allows me to figure out this standard deviation, which is going to be 0.2, 1 minus 0.2 over 50. So that tells me that the standard deviation for M&Ms is going to be 0.0565. So now, I have two distributions. Now this is a little bit of a review. I want to combine two distributions. So in this case, if the shape of one is normal and approximately normal, and the shape of the other one is approximately normal. The shape of their difference, the shape doesn't change. What this says is the shape of that difference is also going to be approximately normal. And that's typically going to be the case. If I have one approximately normal distribution and a second one, when I combine them, that difference, it's still going to be, the shape is still going to be approximately normal. What is the mean of their difference going to be? What is the mean of p hat Skittles minus p hat M&Ms? Well, according to the rules, we do what they say. We're going to take the mean of p hat M minus the mean of p hat S, that's p hat M. So we're going to do 0.216 minus 0.2. So that tells me that the center here is going to be 0.016. And then my standard deviation, the way I'm going to combine the standard deviation is slightly different here, because before what I said is we turn them into standard deviations. We take the standard deviations, we turn them into variances, we square them, turn them into variances. And then what we're going to do is we are going to add them together. But we're going to do something slightly different here. What the standard deviation of this difference is going to be is we're going to take the sample sizes into account. And this is on your formula sheet. The way we're going to do it is we are going to say, we're going to go ahead and do p Skittles minus 1 minus p Skittles over n Skittles plus p hat M&M 1 minus p M&M over the sample size of M&Ms. So what we're going to do is we're going to be plugging in some numbers. We're going to go ahead and plug in 0.216, 1 minus 0.216 over 50 plus 0.2, 1 minus 0.2 over 50. And when I go to the calculator and simplify this, I'm going to get 0.0812. So what this tells me is that this distribution is normally distributed. It's going to be centered at 0.016 with a standard deviation of 0.0812. So then what is the probability of me getting something 8% or greater? What we're going to do is, again, if we kind of drew our curve, we're going to be centered here at 0.016. We're looking at 0.08 or higher. So what we're going to do is we're going to go to Normalcdf. Our lower bound is 0.08. Our upper bound is lots of 9s. Our mean is 0.016. Our standard deviation is 0.0812. And we're going to find out that that probability of having a difference greater than 0.08 is going to be equal to 0.2148. So there's about a 21% chance that we'd end up with a difference of 8% or greater, which is not surprising. So that's kind of what we talked about in class today, a little bit of a review. So hopefully that helps. I'm going to go ahead and have another video that'll kind of walk through the practice as well.